A deep dive on these targeted beamforming panels and how they work. For those big wide panels, you can have up to 128 antennas inside of them, all working together to aim a beam directly at your phone. Older cell towers had a handful of antennas per panel, broadcasting in a wide, fixed pattern. 5G massive MIMO panels pack in 64 to 128 individual antenna elements into one panel. Each one a tiny transmitter and receiver working in coordination. Instead of one wide beam, the system combines all those elements, signals with precise timing offsets to create a narrow, steerable beam, like a spotlight instead of a floodlight, and it can track and re-aim that spotlight at your phone as you move. Every beamform signal produces side lobes, smaller, weaker beams leaking out in directions you didn't intend. Aiming a flashlight, the main beam goes where you point it, but there's always some spill of light around the edges and even behind the flashlight itself. Networks try to minimize side lobes through panel design and signal processing, but they can't be eliminated completely. It's a physical limitation of how multiple antenna elements combine, not a design flaw. Truly wild part is MIMO systems can flip this same principle around and deliberately create nulls, zones of near zero signal, to avoid interfering with other users or nearby networks. Same math as building a beam, just inverted to cancel signal instead of focus it. So one panel is simultaneously steering strong beams at intended users while creating dead zones for everyone else, all recalculated many times per second. Every time your phone connects to 5G, there's a live antenna array doing real-time geometry, building you a beam, leaking a little signal it can't fully contain, and mathematically concealing itself out in other directions, all at once. That's the invisible math behind the bars on your phone screen. Faraday bag for your phone, silver mesh lining. Grab it right now. Brains of the tower. Now, let's talk about them. He's used to process the data, but now they're going to be forwarding it somewhere else. Traditionally, each cell tower had its own baseband unit right there on site, the brain, that processes incoming and outgoing signal, cell data, handoffs, and it runs the tower's core functions. Every tower operated somewhat independently. Modern networks and the way they're increasingly shifting to what's called cloud, RAN, radio access network, RAN, or baseband pooling. Instead of each tower having its own dedicated baseband unit, multiple towers and radio units send raw signal data over fiber to a centralized baseband processing hub, sometimes serving a dozen or more towers from one location. And why would they do this? It's more efficient. Centralized processing can dynamically allocate computing resources across towers based on real-time demand, similar to cloud computing. If one tower has a traffic surge, think like a stadium event and a neighboring tower is quiet, the pooled system can shift processing power where it's needed instead of every tower being stuck with a fixed dedicated hardware. This centralization also changes the failure and security picture. Instead of one tower going down independently, a problem at a centralized baseband hub can now potentially affect every tower connected to it. It also means more of the network's actual thinking is now concentrated in fewer physical locations, which raises real documented industry discussions around resilience and cybersecurity architecture for critical infrastructure, not because of any secret intent, but because centralizing anything critical always changes its risk profile. The tower on the corner might look the same as it always did, but what's actually happening inside it might be nothing. It could just be handing off signal off to a processing center you'll never see miles and miles away. Guys, you watch my page, and if you're gonna cover anything, cover the boys with the boxers. Silver line, 42 dB attenuation, 99.99% of the RF field.